Dear students, welcome to my video lecture. So in this lecture we are going to learn organic chemistry from first semester. So this is the fifth unit. From the general chemistry 1. So the chapter title is Basic Concepts in Organic Chemistry and Electronic Effects. So organic chemistry, it is a chemistry which is based on the carbon compounds. So carbon itself can generate huge number of molecules. So that's why under separate division we are studying about carbon based compounds. So why the carbon itself can generate huge number of molecules? It's because of the unique nature of carbon atom. So carbon, it has a valency of 4 and it has a catenation property. So what is that catenation property? It is a self combination. So carbon can combine with another carbon. So this is a rare type of property. So very limited atoms having this kind of catenation ability, but carbon which can combine with other carbon atoms unlimited way. So that's why the carbon itself can make a variety of or huge number of molecules. That's why we are studying carbon based compounds under a separate topic called organic chemistry. Then the very first organic compound which was synthesized is urea. That compound was synthesized from ammonium cyanide. Now let's see what are the shapes of carbon and carbon compounds. So what you are seeing, this is a framework model, ball and stick model, as well as this is space filling model. And this particular geometry which is called tetrahedron structure. Tetra means 4, you know very well, and hedron means a triangular face. So here the particular structure, so what you are seeing, that is a skeleton form. That is a skeleton form. So if you close this skeleton by triangular faces, you will get tetrahedron geometry. Apart from tetrahedron geometry, carbon also can make trigonal planar geometry and linear geometry, which depends on the type of hybridization involved in the carbon atom. Let's now see the classification of organic compounds. Classification of organic compounds. Organic compounds majorly classified into 2 different types. One is open chain compound, another one is cyclic compounds. Open chain compounds where the carbon atoms are connected in a straight chain or a branched way, whereas in the cyclic compounds, carbon atoms are connected in a ring form. Then under cyclic, where we can have homocyclic and heterocyclic. Homocyclic, which are made up of only carbon atoms, whereas heterocyclic, carbon atoms connected with other atoms also. Other atoms means like sulfur, oxygen, nitrogen. So those type of atoms also may present in the cyclic ring. Again, in both homo as well as heterocyclic compounds, we can have aromatic as well as aliphatic, alicyclic compounds. And in that aromatic, we can have either benzene type compounds or non-benzene type compounds. We now see the first type, that is open chain organic compounds. Open chain organic compounds, or we can also say acyclic compounds. So these are the compounds which are formed by connection of carbon atoms in a straight chain or in a branched chain manner, and those compounds collectively called aliphatic compounds. And what you are seeing, this is an example for open chain compounds. The first one, which is ethane. So here 2 carbon atoms are connected, and in the second one, isobutane, 3 carbon atoms are connected in a straight chain and 1 carbon is in the branch. And the third one, that is acetaldehyde, where 2 carbon atoms are connected in the chain and the Fourth one, acetic acid. Here two carbon atoms are connected in a chain. So like that we can see carbon atoms are connected in a straight chain or in a branched way. So next one, cyclic or ring compounds. Cyclic or ring compounds, where we can have two different types, right? Homocyclic and heterocyclic. Homocyclic means where you could see only carbon atoms involved in the ring formation. And the best examples are cyclopropane, cyclohexane, or this cyclohexene. So these type of compounds where you could see only carbon atoms are present in the ring, right? So these are all alicyclic, aliphatic cyclic compounds. And this tetrahydrofuran is an example for heterocyclic ring structure. Here 4 carbon atoms are along with 1 oxygen present in the ring structure. That is a 5-membered ring, but in that 4 atoms are carbon and 1 is oxygen. And what you are seeing, the next category, aromatic compounds. In aromatic compounds we can have a benzene and non-benzene type compounds. Again we can have that open chain, carbon, only carbon, that is homocyclic as well as heterocyclic compounds. Examples for homocyclic: benzene, toluene, naphthalene, and heterocyclic furan, diophenene, pyridine. Those type of compounds are example for heterocyclics. Then come to this classification of reagents. Classification of reagents. So based on the charge present in the reagent, we can have 3 major categories. One is electrophilic reagent, another one is nucleophilic reagent, third one is free radical. What is this electrophilic reagents? So electron liking species, or we can say electron deficient species. Electron deficient species, these kind of species, they attack nucleophilic center, and these particular species involved in the chemical reactions. Particularly we could see these kind of reagents in the mechanism of the chemical reaction. And these, since they are electron deficient, they may be positively charged or neutral. And these electrophiles are also called Lewis acids. And neutral electrophiles, the best examples: carbon dioxide, sulfur trioxide, aluminum chloride, ferric chloride. These are all examples for neutral electrophiles. So they are electron deficient molecule. Say for example, if you take carbon dioxide, where carbon is connected with 2 oxygen. So most of the, since the oxygen is more electronegative, most of the electron density from carbon shifted towards oxygen. Then carbon feels less electron, so act as electrophile. Similarly in ferric chloride, iron is electron deficient. Aluminum chloride, aluminum is electron deficient. These kind of metal salts used as catalyst in organic reactions as electrophiles. Then positively charged electrophiles: carbocations, proton, oxonium ions, nitronium ions, and nitrosonium ions. These type of positively charged ions also can act as electrophile. So there are electron deficient species, they attack nucleophilic center. So the next reagent, nucleophile. So this is a reagent which has more electron density, electron, or we can say electron rich species. Electron rich species, they attack electrophilic center, that is positive charged carbon atom. Positive charged carbon atom. Since they have electron density, high electron density, they can donate their electron. So we can call them Lewis bases. We can call them as Lewis bases. So then the compounds having lone pair, or negatively charged species can act as nucleophile. Lone pair containing compounds like ammonia, amines, water, alcohol, that is hydrogen sulfide, ether, these kind of molecules. Though neutral, they have excess electron pair, that is lone pair available, so they can donate their lone pair to any reaction site, particularly electrophilic centers. The negative charged species like chloride, bromide, iodide, hydroxide, alkoxide, very famous electrophiles like cyanide. They are good electrophile, powerful electrophile. So these particular negative charged ions, they also can act as nucleophile because they have excess or electron rich. They are electron rich species. They can donate electron to the other atoms, particularly positive charged atoms. So next one, the third, this is the final reagent, free radical. Free radical, it is a neutral species but having unpaired electron. Then how can we define free radical? Free radical is nothing but any species having unpaired electron. The best free radical is oxygen, right? Known free radical is O2. O2 itself a free radical. Apart from O2, we could see many free radicals in the photochemical reactions like H, hydrogen, or methyl free radical, ethyl free radical, hydroxide. Halides ready to form free radical in the presence of light. So these kind of free radicals, they are highly reactive. They are highly reactive and they are ready to react with other stable compounds. These type of free radicals are formed by the homolytic breaking of a covalent bond. When the bond is homolytically broken, there are two free radicals will be generated and that kind of homolytic cleavage is possible in the presence of sunlight. Next, we have seen three different electrophiles, right? So electrophile, nucleophile, free radical. In most of the organic chemical reactions, we can see the involvement of these kind of reagents, more reactive reagents. Now we are going to see classification of reactions. So based on the type of reactions, we can majorly classify the chemical reactions into four different categories. One is addition reaction, another one is substitution reaction, and then elimination reaction, then final one polymerization reaction. So let's now see one by one what are the reactions. So the first one, addition reaction. First one is addition reaction. Here, small molecules like water, bromine, ammonia, so they are involved in the addition process, and this addition reaction mostly occur in unsaturated molecules like alkenes, alkynes and carbonyl compounds. Then we can have two type of addition reactions. One is electrophilic addition, another one is nucleophilic addition. Mostly in alkenes, electrophilic addition is possible. Which means electrophile first attack the alkene, carbon-carbon double bond. Later the nucleophile will come and join. Whereas in case of nucleophilic addition, so this nucleophilic addition is very common in carbonyl compounds. That is, we have a C double bond O. In that, nucleophilic addition is favorable. So first nucleophile attacks the carbon-oxygen double bond. Later the electrophile will come and join. So that, like that we can have two type of addition reactions. And in organic chemistry, these addition reactions are very common. And what you are seeing, this is an example for the simple addition reaction. And in this, ethylene is reacted with bromine. So bromine molecule reacts with ethylene and bromine converts ethylene into 1,2 dibromomethane. And in this reaction, two bromine atoms, right, attached across the CC double bond. So during this process, CC double bond would be converted into CC single bond. And this is a very special reaction because in this, the bromine actually its color is brown in color, brown is red in color. And during reaction, bromine it loses its color. So this particular reaction can be used to test the presence of double bond as well as triple bond in organic compounds. That is, test for saturation, right? Saturation, whether the molecule is saturated or unsaturated. That can be differentiated by using reaction with bromine or bromine water. And this kind of reduction is possible. So this kind of addition is possible in many of the reduction reactions. And this is a second type of reaction, substitution reaction. Second type, substitution. Here, one molecule, right, a small atom or a group of atoms replaced by other group or other atom or group of atom. And again we can have two types, electrophilic and nucleophilic substitution. What you are seeing, the first one, which is nucleophilic substitution, where nucleophile come and replace the old nucleophile bromine. So you will get, so here the alkyl compound converted into alcohol. And the second reaction, which is an example for electrophilic substitution, where hydrogen is replaced by chlorine. And this electrophilic substitution reaction, which occurs in the presence of sunlight. The third reaction, which is elimination reaction. Here, a small molecule like water, alcohol, ammonia or hydrogen halide would be eliminated from an organic compound. As a result of elimination, organic compound would be converted into unsaturated, which means a double bond, that is carbon-carbon double bond would be formed. And in this example, you are seeing elimination of HBr, and this reaction occurs in the presence of alcoholic KOH. After removal of HBr, between alpha and beta carbon, a double bond would be formed. So this is our last reaction, which is polymerization reaction. And in this reaction, so it is a special type of reaction where we can make polymers. So many small molecules combined again and again to generate a long chain, that is a network-like molecule, so which is called a macromolecule. So this macromolecule has variety of applications, and so that's that kind of repeated combination of small molecules which are called monomers. So that is called polymerization reaction. And what you are seeing an example for the reaction of polythene formation reaction. In this ethylene molecule again and again combine to generate polyethylene. Polyethylene, it is highly useful in the day-to-day life. So I think, so that's all. So thank you so much.